What is 46?
I have it right. It's g of x equals ln to the quantity 1 plus x squared.
I wasn't right. So g of x.
Ln 1 plus x squared. And then f of x is x divided by 1 plus x squared. And you also have to find the interval.
Okay. So we want to write a power series for g of x, right? And so the nice thing about this is they're telling you what function to build the power series for. So like for the exam, you'll have to figure that out. So this will be up to you to determine, okay, on the exam. But they're giving it to you. All right? So, but how would we know that? Well, natural log the derivative of natural log is basically 1 over that. And when we take 1 over that, we get something like our a over 1 minus r. So that's, and then why did they put the x on there too? So that when we do the antiderivative, it's convenient, right? It's convenient for the antiderivative. All right? So the antiderivative of that will be a lot like natural log of 1 plus x squared. So if we can find the power series for x over 1 plus x squared, then we'll take the antiderivative of it, and we'll have something very close to g. And we'll just have to clean up the mess a little bit, right? So what is 1 over x? I'm going to go a little bit fast here. A is x. R is negative x squared. So I think this is the geometric series for so like in your web work and then on the exam, you'll have to come up with that function f. And that's like what we did on Friday. It's not going to be given to you. You have to come up with this function f that you can write easily as a power series because it's in the form a over 1 minus r. And also, it gets us easily either by derivative or antiderivative to g. So you have to come up with that. So what is this? This is the same as x to the negative x squared. So let's factor out the negative. So we got a negative. We got a negative 1 to the n, and then we have x to the 2n plus 1. So x times negative x squared all to the n is the same as negative 1 to the n, and then x to the 2n plus 1. And hopefully our algebra, our rules of exponents are good. You can do that and see that. So when n equals 0, we have x, check my math, we have x. When n equals 1, we have x cubed. When n equals 2, we have x to the 5th. Check my math. Does this look right? I don't want to dig a hole for myself. So do you agree with what I wrote there for the terms? I got one nod. If you think there's a mistake, don't hesitate. Okay, so what am I going to do now to f to get something like g? Antiderivative, right? We're going to do antiderivative. So integral of fx dx is going to be natural log 1 plus x squared. And then we think about taking the derivative of that. Is the derivative of that exactly what we started with? No, we also need a 1/2. Okay, so now antiderivative. Antiderivative of this. With respect to x now, with respect to x. So this negative 1 to the n just stays. Okay, with respect to x, it's going to be x to the 2n plus 2 all over 2n plus 2. So everything, we're doing antiderivative of everything. Antiderivative of f is integral of f. Antiderivative of x over 1 plus x squared is the 1/2 natural log. Then antiderivative, and then antiderivative here of x is 1/2 x squared minus 1/4 x to the 4th plus 1/6 x to the 6th. And then we can do a quick check to make sure that our terms agree with what this, since we're doing them separate, right? So I got this from this, and I got these terms from these terms, so let's make sure that these agree, right? So if I plug in n equals 0, do I get 1/2 x squared when I plug in n equals 0? Looks like I do. When I plug in n equals 1, do I get negative 1/4 x to the 4th when n equals 1? Looks right. When I plug in n equals 2, do I get 1/6 x to the 6th? Yep, so it looks like everything's good right now. So is this the function g? Is this the function g? And if not, what adjustment do I have to make to this to make it the function g? So I'm going to take this and divide this by 2. And that will give me g. So this is divided by, right? This is g divided by 2. What I just wrote here is g divided by 2. So to get g, multiply by 2. So we're just going to everything times 2. And we have g. And by multiplying by 2, I think it just takes those 2 out of the denominator. Is that right? I get x to the 2n plus 2 over n plus 1. Right? Because I can factor a 2 out of the denominator and then times 2, and the 2's go away, and I have n plus 1. So I think that's the simplified version. And then I'm going to get x squared minus 1/2 x to the 4th plus 1/3 x to the 6th, etc. Check my math. Do you agree with my math? Anybody have a question? So this was a nice kind of lead in, because in these problems they gave you what you're going to use and initially set up to then work towards the power series for the function that you want. From here on out, that's up to you to figure that out. What you're going to need so that either derivative or antiderivative will get you what you want. Last chance for questions on this one. Okay, so I want to quickly talk about the example we had at the end of class last time, which was this: x squared natural log 1 minus x squared. So I've graphed that function. This is the blue graph here. I've graphed that function, x squared times ln of 1 minus x squared. Here's what we got for our power series. So a similar example to what we just did for the homework. We got this in class. So I just wanted to show you quickly. And so if we write out the terms of that, n equals 0, n equals 1, n equals 2, n equals 3, etc. That's what the sequence looks like in its terms. So we can see what happens with, if I just take this first term of the series right there and graph just that first term, that would be for capital N equals 0. So if we went from little n equals 0 to capital N equals 0, we just get the first term. And if we graph that, that's what that looks like. So you can see that it's trying to be like the blue graph, but it's not great, right? It's not a great approximation. What's the limit of these terms? So what's the limit of these terms of this, like as a sequence? What's the limit of these? Who remembers the most important thing about series from the beginning? We have a convergent series. Uh-oh. If you have a convergent series, what? No, series. Series. Convergent series means the sequence has to converge to 0. That fact is not enough. But if you have a convergent series, then that sequence must go to 0. You must eventually just be adding on essentially 0 in order for it to converge, right? Because you're adding an infinite number of things together. So every time I add on another term of the series, it's going to get closer and closer to the value of the series. So if I go from n equals 0 to capital N equals 1, now I'm adding the first two terms. Now that's the first two terms, capital N equal to 1. And so it's a little better approximation of the actual graph. So every time I add on a term of the series, watch the red graph. There's capital N equals 2. Capital N equals 3. So with each term that I add on, I'm getting a better and better approximation of the whole series, which is the function, x squared ln 1 minus x squared. So when I add more and more terms on, the graph of our series keeps getting it's converging on the actual function, the blue function that we were writing as a series, right? So here's the first 17 terms, or up to n equals 0 to 17. This is the graph I get when I graph that polynomial of the first 17 terms. Pretty dang close to the function that we were writing the series for to start with, x squared ln of 1 minus x squared, the blue one. I think I've got it going up to 20 here. So you see that it's a very good approximation close to 0, and then still very good, but now we can see there's still a little bit of difference out here at the edges at -1 and 1. We can see that it's still not quite the function, but doing a very good job of approximating the function. So that's what we're doing. We're writing functions as series, and so by taking more and more terms of the series, you get a closer and closer approximation of the function that we were writing. So those are called partial sums, right? Partial sums. The more terms you take in a partial sum, the closer it is to the actual sum of all infinitely many terms. Okay, so let's keep talking about the same idea here, writing functions as series. So there's these things called Taylor and Maclaurin series. So far we've written functions. As series if those functions were of the form a over 1 minus r, or related to that by derivative or antiderivative. Okay, well that's a very, very narrow class of functions that look like a over 1 minus r, or related to a over 1 minus r by either derivative or antiderivative. That's a very, very narrow class of functions, right? It's got to be in this very specific form. So what Taylor and Maclaurin series are able to do is they're able to write any function as a series. Okay, so we can write any function as equivalent power series. So we go from this, what we've done so far being this very restrictive, narrow class of functions that we could do, to now like any function. Any function, we're basically rewriting it as a polynomial. And so if it's a polynomial of finite number of terms, that'll be an approximate function. And if you extend the series out to get all infinitely many terms of the polynomial, then you'll have the actual function. So let's talk about Taylor series first. The Taylor series looks like this. Okay, and so by fn of a, we mean the nth derivative. The nth derivative evaluated at a. So fn of a is the nth derivative of f evaluated at a. And so a is what's called the center, right? So it's gonna work its way out from the center. We talked about interval and radius of convergence. So those always had a center, right? The interval of convergence always had a center. And so that's what A is. A is going to be the center of whatever interval it's going to converge on. Okay, so it's not a very complicated thing, right? We have the nth derivative taken at A over n factorial, and then times x minus a to the n. So this is a power series. It basically creates a polynomial, an infinite polynomial that can approximate any function. So I want you to write out the terms. So what you see that, and you think what, right? You see that and you think what? Practice, write it out. So the 0th derivative is just the function, just evaluating the function at a. Okay, so this is what you should have had. And if you remember, what did we say 0 factorial is?
1.
Yeah, it's 1, right? So 0. Remember that 0 factorial is 1. So this is what you should have written. This is what you should have written. Again, the derivative. So each one of those is the first, second, third derivative, and then that derivative evaluated at a. So to build a series, then we're gonna have the function. Suppose we want to do sine of x. Okay. So then f of x would be sine of x. What are we gonna do? We're gonna have what we want to center it around. We're going to take the different derivatives of sine, plug in a into those derivatives, and then we just write it out. We write it out, and that's going to build a polynomial. That if you had all infinitely many terms of that polynomial, you'd get exactly the function sine. You'll see. We'll do it. So a Maclaurin series then is the same thing as a Taylor series, but the specific case when a is 0. So when A equals 0, it's called a Maclaurin series. So it's a type of Taylor series. So now I want you to so write the general form of the Maclaurin series, both as in summation this way, write the Maclaurin series this way, and then write out the terms. But you want to write it totally simplified, right? So everything as simplified as it can be. So write out the Maclaurin series in the summation form and in the expanded form. Okay, hopefully that's easy. X minus 0 equals. So you're not going to write x minus 0, right? What are you going to write? Everybody? X, right? X minus 0 is just x, right? You don't write x minus 0. So we're going to get this. Here's the Maclaurin series. This is what you should have wrote. The nth derivative evaluated at 0 over n factorial times x to the n. That's the Maclaurin series. Okay, so when you're building a Taylor-Maclaurin series, it's really helpful to have a table. So this would be particularly for Maclaurin series. So let's write the Maclaurin series for e to the x. E to the x. So what are we doing? We're building a polynomial that essentially is e to the x. And if we have a finite number of terms, it'll approximate e to the x. If we have all infinitely many terms, it will be e to the x. Okay? So what we can do is come over here and for different n values, so the 0th derivative, the first, the second, the third, let's go do the fourth, we're going to need each of those derivatives evaluated at 0. So let's start with the nth derivative. So what is the nth derivative of e to the x? Well, that's just the function itself, right? The 0th derivative is just the function itself. So now this refers now and the first derivative. So what's the first derivative of e to the x? E to the x. What's the second derivative of e to the x? Okay, so, and that's just going to keep every derivative of e to the x is just e to the x. And then we're going to evaluate each of those at 0. That's the number we need to build the series, right? We need what the derivative is evaluated at 0. What's e to the x evaluated at 0? 1. And since it's always e to the x, it's always going to be 1. So all of these values are just 1. F of 0, f prime of 0, f double prime of 0, f triple prime. For this particular function, e to the x, it's just 1. Since all derivatives of e to the x, they equal 1 and x equals 0. So now, can you set up the series? Can you set up the series? So this will always be 1, and then we'll have n factorial and x to the n. So e to the x is just going to be x to the n over n factorial, because all of those derivatives are just going to be the value 1 when they're taken at 0. So any partial number of terms will approximate e to the x. The more terms that you take, a better approximation of e to the x that you will get. And then if you take all the terms, you'll get e to the x. But we should actually, what we should say is, we need a interval or radius of convergence. So to get that, we do our normal thing. We could do the ratio test. So do the ratio test on this. You get x to the n plus 1. Do it fast here. And we have one more x in the numerator than the denominator. And then what's n factorial over n plus 1 factorial? We should remember that. That's just n plus 1 in the denominator. So now we've got x over n plus 1. And we're going to take the limit as n goes to infinity. What is that limit as n goes to infinity? And when does the ratio test tell us that we have a convergent series? For what values of x is this limit less than 1? For what values of x is this limit less than 1? That's the question we're asking. All of them. It doesn't matter what x is. You always get a limit of 0, no matter how big of a number of x you choose. Because n plus 1 will always get much, much bigger than whatever x you choose as n gets very large, approaches infinity. Okay? So, what is the radius of convergence? Or the interval of convergence is all reals. Meaning that if you took every single term of this infinite polynomial, you will get the whole function e to the x. And if you have a finite number of terms, it'll be an approximation, and which will get better and better as you take more terms. So let's see that. Let's see that in action here. Questions on building the Maclaurin series for e to the x, or finding the interval of convergence? Come back to that. So let's go back to our okay. I was almost ready. Not quite. And make that one blue. Reset the graph. Not showing anything. Okay, so here is e to the x. Here's e to the x. I got it in blue. And what are we doing? We're doing the Maclaurin series that we found. X to the n over n factorial. So if I take the first term, capital N equals 0, it's only right for one value, right? It's only right at that point 0, 1. Now if I take the first two terms of the polynomial, so what is this right now? This is 1 plus x. That's 1 plus x as an approximation to, should be drawing this in red here, as approximation to e to the x. The first two terms of the Maclaurin series for e to the x, okay? So now if I add on x squared, here's what it looks like. First three terms. Okay? First four terms. See what's happening. With every term that you add, it gets a better approximation of the blue curve. So let's zoom out a little bit here. Let's see more. All right, that's good. And so that's what? We got the first 4 terms. So that polynomial that I've written, that's what you're seeing in red right now. And you see that near 0, it's doing a really good job of estimating e to the x, but then you get away from 0 and it's not doing so well. But with every additional term that we add on, every additional monomial that we add, it's gonna fit itself to e to the x better and better. So here's the first 5 terms. So let's just take it here. Let's do. So notice it's flipping up and down, but it's flipping up and down further and further. So here's the first 21 terms. The fact that this is black here means that the red graph, our approximating series, is right on top of the blue e to the x function. And so as you add more and more, it's going to do better and better further away from 0 as you add more and more terms. Can I get to see this peeling off from? Yeah. Yeah, I just didn't write it out. Yeah, thank you. So this one was actually, so this is 2 factorial. I've got this doing it right. I just didn't write it down right. Thank you. So it looks like for this is the first 21 terms. It's pretty good, probably from -8 all the way to 8. Probably in that whole interval, it's probably very, very, very close to e to the x. But then it will peel off. But then the more terms we add, the better it will approximate e to the x further and further away from 0. Okay, and like we said, if you could add all infinitely many terms of this x to the n over n factorial, you'd have exactly the function e to the x. Okay, let's try another one. Or let's talk about something here related to that. Okay, so one thing this is helpful for is polynomials are they're nice to work with, right? So they're very convenient functions to work with. Derivative, antiderivative is very easy, okay? And so because they're convenient functions to work with, that's a reason why you might want a what's called a Taylor polynomial, which would be like an approximating polynomial to some non-polynomial function, like e to the x. Okay, so for instance, we could use this polynomial now to estimate e to the 4th. So how would we estimate e to the 4th? Well, that's when x is 4, right? So if e to the x is this polynomial here, then what would e to the 4th be? Or an approximation of it. We could write out an approximation to e to the 4th as what? 1 plus what? Four, right? Plus what? See, it's still a function. It's still the function of x. So let's take it out to this many decimal places and see how close it is. So this is approximate now. This is not equal. If we stop, as soon as we stop and we don't keep adding on terms, we have an approximation to e to the 4th, and not exactly e to the 4th. So let's see what that is. It's not what I wanted to do. All right, so 1 plus 4 plus, what do we say, 4 squared over 2 factorial. 4 cubed over 3 factorial. 4 to the 4th. Let's do one more. 4 to the 5th. Okay, so if I if I take 6 terms, I get 42.8667, and let's say what exactly e to the 4th is. So not close, but with every term, so 42.8 versus 54.6, but with every additional term that I add on, it's going to get closer and closer, and then if I were to add all infinitely many terms together, I would get exactly e to the 4th, 54.5982, yada, yada, yada. Okay, if it was like e to the 0.5, something close to 0, right? This is centered at 0, Maclaurin series centered at 0. So if I took a number closer to 0, we'd get a better approximation much quicker. Because we saw that happen, right? We saw that it was a really good approximation in the middle, and as we added more terms, then it started getting better on the ends. So if I started with e to the 0.5, you'd get a much better approximation with much fewer terms, because you're closer to that center point 0. Okay, and so then we can also build off of our e to the x function and find other functions. So for instance, because we have e to the x as a polynomial, we could very quickly write a function for e to the minus 3x and x squared e to the x. So try those two. And then if you're done with those, try this one. So using the e to the x polynomial that we found, what would be a series for e to the minus 3x? And what would a series be for x squared e to the x? And then if you're feeling confident, what about this last one? What would be a series for e to the x minus 1 minus x? Go, see if you can do it. So you're not starting over. The whole point is you're using the e to the x that we found. Just write it down, right? You just write it down. If e to the x is that, then what's e to the minus 3x? You just write it down. It's just the idea of function, right? The idea of function. Okay, so the point is, look at this one, x squared e to the x. If we were doing this from scratch, we would need several derivatives of x squared e to the x and then plug in 0 to those. But immediately we'd have to do the product rule, and then we'd keep having to do the product rule more and more. So those derivatives would kind of get nastier and nastier, more and more complicated, because we'd have repeated product rule and the terms would start growing. So the beauty of this is we've got this easy one, e to the x. Well, we could just multiply that one times x squared, and that'll give us the right series, rather than starting from scratch and calculating all those derivatives on x squared e to the x, which would kind of blow up fast. Does that make sense? So the convenience here is find the Maclaurin series just for e to the x, and then multiply by x squared, and you're done. Okay, so we won't do this, but I'll just give you a hint. So notice, in this one, we know what e to the x is. Notice that the first term of e to the x is 1, and the second term is plus x. And so this is asking for what would the series be for e to the x minus 1 minus x. And I'll let you think about that. So the hint is that the first two terms of e to the x are 1, positive 1, and positive x. So what would e to the x minus 1 minus x be as a series? Okay? So let's do the Maclaurin series for cosine 3x. Here we go. Okay, so the nth derivative, the 0th derivative, is just the function. Okay, first derivative of cosine 3x. Negative 3 sine 3x. Second derivative. Negative 3 squared cosine 3x. Then, third derivative would be positive 3 cubed sine 3x. Check my math. And then we'll have 3 to the 4th cosine 3x. One more, be negative 3 to the 5th sine 3x. Did I do the math right? Okay, now what we need is evaluated at 0. Evaluated at 0. So, cosine of 0. 1. Negative 3 sine of 0. 0. Negative 3 squared cosine of 0. Negative 3 squared. 3 cubed, sine of 0. 0. 3 to the 4th, cosine of 0. Positive 3 to the 4th. Negative 3 to the 5th, sine of 0. 0. We'll do one more. It'd be negative 3 to the 6th, cosine of 3x will give us negative 3 to the 6th. So what will it be? It'll be 1 over 1 factorial times x. No, times, that's it. X to the 0 is 1. All right, then plus 0. Because the first derivative is 0. And then minus 3 squared x squared over 2 factorial. And then the next one will be 0. And then plus 3 to the 4th x to the 4th over 4 factorial. Plus 0. Then minus 3 to the 6th x to the 6th over 6 factorial. So I'm just taking this column right here and putting it in for that right there, and then writing all the terms out.
The first term should have been over 0 factorial.
Thank you.
It's the same if
Yeah, you're right. That's right. Okay, so you get 1 minus 9x squared over 2 plus 81x to the 4th over whatever that is, 24, minus, I don't know, over 720. So what did we just find? This is a polynomial representation of cosine of 3x. The more terms you add, the better the approximation of cosine of 3x. Okay, listen carefully. Announcements. So our next exam is this Friday. So I'm going to post review material today, and you have a web work due Wednesday. And I'm going to add some problems to the web work. Okay, so based on what we did today, just a few. And then on Wednesday we'll finish up the Taylor and Maclaurin and do a little bit of review. And then, like I said, the exam is Friday. And then are you having another review session?
And then I'll do a review session on Wednesday from 5:30 to 7 in Wexler A303.
Wednesday at 5:30, he'll have a review, and then that will be on Piazza, right? And he'll announce that on Piazza as well. So check Blackboard for all information about homework and quiz or exam preparation.